going to start to talk about the ideal filters. Uh, the last time we started to talk about the filters, and I explained that we usually use the filters when we have a signal and we somehow we want to manipulate the signal. In other words, usually it's like that. We have a signal in the time domain, and we can bring it, either we can keep it in this time domain or bring it in frequency domain. Assume we convert it to a frequency domain. And then there are part of some frequency in the signal that we want to keep it, and then there's a part of the frequency in the signal that we might want to remove from the signal. For example, I said when you're using your cell phone and you're talking on the phone, so the microphone on the phone is gonna capture your voice, but also it's going to capture the background noise or the background voices, the background sounds. So when you can use the filter in a way that keep all the frequencies that related to your voice, just keep them, and then remove all the frequencies that are related to the background noise or background sounds. So by doing that, uh, the sounds that's gonna sense over the phone is only gonna have your voice and doesn't gonna have the background voice. So usually that's how we use the filter. So to keep part of the signals that we are interested in, and to remove part of the signal that we are not interested in. As I said previously, we can do this filtering in the time domain or um, in the frequency domain, or we can do it uh, using the analog circuit, or we can use it by digital filters using the computers. Anyway, so one form of that is the ideal filters that today I'm going to talk about it. That is ideally what type of filters we would like to have. And there are four types of filters that I'm going to discuss uh, today that usually they call the ideal filters. Uh, just know that is usually we may get close to this ideal filter, but usually we can't get the ideal filter in the real world. But when we are designing the filter, we usually want to get as much close to this ideal filter as possible. And the ideal filter that I'm going to talk about them today is going to be in the frequency domain. So assume that we have a signal in the frequency domain, then we convert it to the time domain. Then we want to use the filter to filter out those that signal in the frequency domain. The very first type of the ideal filter that we have is that assume if this is the um, and before saying that, let me just mention something. So if we are in the frequency domain, usually we know that if we assume the signal is V, the output signal is the filter or the response function of the filter, and then times the uh, input signal. So simply when we want, if we are in the frequency domain, when we want to filter, if you have the signal in the frequency domain, we just multiply it by the filter itself, or the um, as I said, the frequency function of the filter, but sorry, the transfer function of the filter, or simply just this is the filter in the frequency domain. This is the input signal in the frequency. Just multiply them, and by multiply them, we are going to filter out the input. We are going to filter the input signal and get the output signal. So, what are the ideal filter? The very first type of the ideal filters is going to look like this. So, if I have this HF, the magnitude of the HF here and then here I have the frequency. So everything is going to be in frequency. So this is the frequency, which is usually in hertz, but I would say here frequency, and this is the magnitude of this transfer function of the filter. So then if we have that, the ideal filter for the first type of ideal filter look like this. So it goes all the way up here, then goes down to 0, and then goes then it stays 0 for the rest. So this is going to be 1. So it is 1. Then it's 1 all the way through until it gets to the frequency that we call it the, for example, here I call it the FH, or it's basically the cutoff frequency. So, and then it becomes 0. So this frequency, I just mentioned that. So it's going to be the cutoff frequency, and here is the higher cutoff frequency, but so it's the cutoff frequency. So if you look at that here between 0 and the FH, the filter is 1. So look at this equation. So it's going to be 1. So basically the input signal is going to be equal, the output signal is going to be equal to the input signal, because the HF is going to be 1 between 0 and FH. And then if the frequency is larger than FH, the output signal is going to become 0, because the filter is 0. So it let pass all the signal is less than the FH, and it filter out all the signal that's larger than FH. So that's why they call this filter a low pass filter. So this is the low pass. So it's a low pass filter. So it's the ideal low pass filter. So why? Because all the frequency that they are smaller that cutoff frequency, it just let it pass. So it's a low pass. So it let the low pass frequency goes through, and all the frequency that are larger than cutoff the frequency, it's just gonna make them 0. So it cut them out there. So what are the use of this type of filter? In case that we have the frequency that there are some higher frequency that we don't want them. Usually it's a noise. Usually the noise are very high frequency in the domain, and we don't want them. So we use that low pass filter. So it let all the filters let all the signals that are good pass through, and then it filter out all the noises that we don't want, all the high frequency noises. So it remove it from the signal. The second one, which is completely the opposite of the one we have here, is like this. So if I have the filter look like this. So again, if this is the transfer function of the filter, and this is the frequency, this time it starts from 0. So everything stays 0. And then by the time we get to some, for example, let me go a little, so if come to some cutoff frequency, again, this is I just call it, so, and we reach to cutoff frequency. So it's 0, and then we get to the cutoff frequency, it goes up, and it goes up, and then it stays 1 there. So So it is 0 between the 0 and the FL, and then is 1 when the frequency is larger than FL. In other words, if the frequency of the signal in the input signal is between 0 and the FL, because it is 0, it's going to completely filter out. So the output signal doesn't have any signal between 0 and FL. And by the time that it gets to the FL, it lets all the signal pass through without changing them. So all the signal that are larger than, that has a frequency larger than FL, just pass through without being changed. That's this type of signal is called the high pass ideal filter. So um, in, contrary to the first one, that it lets the lower frequency pass through and remove the higher frequency, this one is removing the lower frequency and let the higher frequency uh, pass through in the system. The next one that I want to share, so these are the first two. The third one, so assume we have again the so it's going to be the frequency, and this one is going to be again the magnitude of the filter transfer function. So this time, what we will do that is that we start from the 0, and by the time we get to the FL, we go up there. We go to 1, then we stay equal to 1 for up till to get to the FH, and then we go back to 0 again, and we stay 0 there. And this is going to be the FL, and it's going to be the FH. So this one, if you look at this one, is that it only let the signal that has a frequency between FL and FH pass through. And if the signal has a frequency less than the FL or larger than FH, is going to be filtered out. Only that part of the signals goes through. So if you have a signal that we want to, for example, have the very specific part of that signal, we can use this filter. For example, assume that there's a music, and we want to specify just to remove all the other sounds but one sounds. So we can go and see that sound, what's the frequency for that sound, and keep that part, and then remove what the rest of the signal with the other frequency from the signal. So that's how that is gonna do that. And again, these two are the lower cutoff frequency and the higher cutoff frequency. So both of them are again cutoff frequency, and this time is the band pass. So basically, it let a band of signal pass through. So there is a band pass filter. So that band of is a band between FL and FH pass through, and then reject everything that is either less than FL or larger than FH. And the fourth type of the ideal filter is just the opposite of the third one. So if I have again this, this is going to be the frequency, and the transfer function of the magnitude of the transfer function of the filter. In the previous one, we let the band pass, so it's very specific through between two frequencies. We just let that go through, and this time we are gonna just do the opposite of that. So it's gonna be stay 1 until we reach to the FL, then it goes down to the 0, and then it stays 0 then it goes back up, and then it stays 1. So this one is going to be the FL, and this one is going to be the FH. So this time, the difference between this time and the previous time is that it let either if the frequency is between 0 or FL, or the frequency is larger than FH, it lets it pass through. Otherwise, if the frequency is between FL and FH, it's gonna reject it, and because of that, they call it the band reject filter. So it's gonna be the band reject. So it's gonna be the band reject ideal filter. So these are the main 4 type of filters that usually we try to design and try to work with them. So if we look at them, these are, as I said, the ideal filter, and usually we cannot get to that type of you cannot get to any of these filter. What we try to get as much as close as possible when we are designing a filter to any of them. So in last word is like that. So we have the, if I want to show the filter, so I have the filter like that. So whatever that's in that filter, so it can be analog or digital filter. So if it's an analog filter, it's basically a circuit, and that circuit has 2.2 terminal input, and it has 2 terminal output. So I connect the, for example, the V in here to these two. So it's going to be connected to these two, and this filter can be either of these 4 or combination of these 4, and then we have the output filter. Remember, we can either use any of them separately, or we can combine them one after another in case that to do if we are looking for very specific type of filter. So we might pass through the whole signal through, for example, the low pass filter, and then pass it through the band pass filter, and then pass it through the high pass. It depends on what we want, what we need to do. We can just combine them in any order that gives us whatever we actually need to be as the output of that. So that filter can be either of this one or the combination of this one. If it's going to be the combination of this one, it's going to be, they call it the cascade filter, and basically it's similar like that. If you put this one first and the second one and this one second into that, you multiply these 2 together. So if you combine them, it's like that, you multiply them just by each other. So these are just the introduction to the ideal filter.